So this locomotive runs on a steam engine with a power output of this, an efficiency of 12%. Calculate the rate at which heat is being delivered to the steam engine. So remember that an engine, a thermodynamic engine, works like this, right? This is QH, this is QC, and this is W. So efficiency is like work output over heat input. Okay, so then if we want to know the rate at which heat is being delivered to the steam engine, let's take a time period of 1 second. Yes. Let me just check. Should never be too careful. Yes, it is. So in 1 second, the power output, that's this, right? The power output here is 4.5 megawatts. Right? That's the power output. So we're looking for the QH. So then we just use this equation. So then we get QH is equal to W over E, or 4.5 times 10 to the 6th divided by 0.12. 0.12 is what? 1/8, so it's going to be like 8 times that. So it's going to be like 36 megawatts. That's my guess. All right. Just so that we can all be lazy, you don't have to use your calculators. If you look at this. Okay, 38 megawatts. I was off by a little bit. All right. Then we can go to part B. Calculate the magnitude of resistive forces acting on the locomotive when it's moving at a constant speed of that. Okay, so if you're moving at this constant speed, let's see, we don't know the mass. We know that the power, the work, well, the work is equal to force times distance. We know that. And we know, let's see what else. We know the work output is, what was it, 38 megawatts per second. We know that it's doing that per second. Dork, sorry. It's not doing watts per second. That would be weird. It's doing joules per second. So we're doing this much work in 1 second. Oh, yeah, okay, sorry. I think they lost last night. He's messing up my brain. Yeah, power is, we know that to be work over time, right? But it's also force times velocity. So then we could just use this. Force is going to be power over velocity. The power was 38 megawatts, and then the velocity was 7. So it comes out to be, whatever that is, 5 something. So if we go here, okay, 6 as well. But yeah. All right, then suppose the gas and the heat, so this is the PV diagram for what's going on in there. What does the area bounded by the path A, B, C, D, A represent? So A, B, C, D, A. So what does this mean? What is that? Well, this is what's happening to the gas inside the steam engine, right? So if we start at A, what's happening? Yeah, this is the amount of work done by the system, right? Yeah. Okay, and we can see what's happening here. First, literally what happens? That's easy. Ray, what's literally happening from A to B? Yeah, the pressure is rising, without the volume changing. So what do you know must be happening? How can you increase pressure without changing the volume? Yes. So we know that heat is being added, and that's making the steam pressure up. Okay. Then what happens here? Yeah, the gas stays at this temperature and expands. So then they allow the the piston. So it's like there's this little cylinder, little space, and then the steam inside there gets heated up. When that gets heated up, that pushes the piston out. That's what happens here. Boom, that piston goes out. When it reaches its maximum part, what happens then? It stays at the same temperature, but it drops in pressure. I'm sorry, the same temperature, the same volume, but it drops in pressure. So then heat was released, and then now it gets compressed back to its original state. So this is the work done by the gas. So it's like the gas expanded, so it pushed the piston. And then since work is pressure times the change in volume, we know that the area under BC, all the way down to the axis, the x-axis, is the amount of work done by BC, by the gas. And then when it went from D to A, that's when the mechanical system recompressed the air. You get what I'm saying there? So it squishes it back to its original volume. Okay. Now, why does it stay at the same pressure if it's squishing back to its original volume? How is that possible? What must be happening here? Because, you would imagine, right? Like, here I have a certain volume, and then I compress it. I get it smaller. So I would expect the pressure to go up. But why is it that I squish it, but the pressure doesn't go up? Yeah, you must have decreased the temperature. Does that make sense? Okay, so this one increased the temperature, then that allowed it to do work. And then the mechanical thing decreased, or the pressure decreased, and then the volume decreased. So this process, we're losing heat. That's what it makes it good. All right, so I would say the work done by the gas. So we take a look. Yeah, it's work. If you say, oh yeah, this is the work that could be calculated. Oh, whoops, that's the second part. Here, let me see if they give us this work. Yeah, I guess they're being okay. Oh, nice. I thought they were going to make you be specific about the sign, right? Because if you'll remember over here, right here, W represents the work done on a system, right? The work done on a system, which means if this gas does work, the sign should be what? What's that? So this says, for mechanics and thermodynamics equations, W represents the work done on a system. Okay, so if if this goes in Jenny's hand and then drop her hands down on the table, that is work being done on her. Get it? By the environment. Now lift it back up. That is work done by her onto the environment. Do you get what I'm saying there? So they're saying this is positive, and when she does work, it's negative. Get it? So it's like you work out, you get tired, it's negative work. So just a little side note, I kind of thought they would put that in there. And in this case, who did the work? Oh, there you go. Yeah, who did the work? This work is done by there's only two choices, gas or system. So either the system moved or compressed the gas, more than the gas expanded into the system. Which one's bigger? The gas expanding or the gas contracting? Right? Okay, where is the part about the gas expanding? It's this, it's this area right here. That is the area that is the work of the gas expanding. Does that make sense to everyone? On your formula sheet, does it say work is negative P delta V? Yeah. Okay, that's why work is negative P delta V. Because when the gas does work, it's negative. This, right here, can you see that? That area there is the work done by the system. So you see, when you want to know who did more, you just subtract the two. Right? And then, if you're doing multiple choice questions, just remember, when this is clockwise, that means the work is done by the gas. If this is counterclockwise, that means the work is done by the system. So this means the work is done by the gas, therefore it's negative, right? If this graph is this way, counterclockwise, right? Then that means work done by the system, which is positive. Oh yeah, so should be. Sorry, I'm emotionally crushed.
Was it that bad?
Yeah, it was bad.
Because Kevin wasn't playing.
You know, that's tough because he was the biggest part of the leadership of the team, like, you know, getting everybody up, trying to keep everybody up. But yeah, it just didn't matter from soup to nuts. I mean, they tried, like, you know, our guys tried. So I'm proud of them. I'm proud of their season. It makes me happy. Like, it makes me positive for next year because if we face that same team next year, we will beat them. But I'm disappointed in that we just picked this game to play our worst game of the season. Yeah, it was just brutal. I mean, I think in 3 sets, I think that team had maybe 15 kills. Right? That probably doesn't mean anything to you, but because volleyball is the only sport where your mistakes cost you points. Every other sport, your mistakes don't cost you points guaranteed. If you get a turnover in basketball, they don't score, for sure, right? If you fumble in football, they don't score for sure. But in volleyball, if you fumble, boom, they get a point. Yeah, it's a huge amount of pressure. So every single ball is a point, and we just gave them point after point after point after point. You know, so, and it basically, every time we passed well, we killed and got a point. So we could, every time we ran offense, it was like, boom. So we were just a better team than them. But for some reason, up here, it fell apart. It's fine. I wouldn't trade him for any other team, but yeah, it's just frustrating to not see them play at their best. Because if we would have even played at 50% of our best, we would have beaten. So, all right. So this represents the work, right? That's what they're looking for. Calculate the power output of the engine. Okay, so notice what they say here. They're saying this is 4 cycles per second, right? So just calculate the work, which is negative P delta V, right? And then that's in 1. So then if you then put that into 4 works per second, that will equal the power. Does that make sense? Okay, so then, yeah, just do that, right? This pressure right here is 2 times 10 to the 5th. This work here is 0.4 cubic meters. I don't know if they would actually do this to you. Maybe in the multiple choice, this has to be cubic meters, that has to be pascals in newtons per meter squared, right? A newton per meter squared is called a Pascal. So if you see pascals, that's what it means. And if you get a volume that is in actually liters, remember you have to convert to get the work. Because how many liters are in a cubic meter? There are 1,000. Because a liter is equal to a cubic decimeter. And remember, a decimeter is how much of a meter? Yeah, 1/10, right? So then that means in a cubic meter, there's 10 times 10 times 10. So that means 1,000. So there are 1,000 liters in a cubic meter. So if they give you something other than pascals, you have to make sure you have it the right way. And if they give you something other than cubic meters, you have to have that in the right way. Yeah, but then since this is cubic meters and pascals, I can just multiply. And so I get whatever, 0.8 times 10 to the fifth. So that'd be 8 times 10 to the fourth, right? And so that's going to be 4 times 8 times 10 to the fourth per second, or 32 times 10 to the fourth watts. At least that's what I'm thinking. Let's see if I'm right. Yeah, 32 times 10 to the fourth is the same thing as 3.2 times 10 to the fifth. So we're good there. And then indicate below all the processes during which heat is added to the gas in the heat engine. Well, we know, kind of already talked about that. Where to go? Oh yeah, AB, we knew that was heat had to be added. BC, oh yeah, sorry. BC, we knew that heat had to be added because the volume increased, right? The volume increased without the pressure changing. So how would you get the volume? So heat was here, and this is, that's what we talked about where we said this part, we talked about heat was removed, right? Heat was removed. So, it just kind of makes sense that this part is where heat was added. So hopefully that makes sense to you about that. And should I make this 3 small videos or 1 big one? 1 big one? Okay, here we go. This is the Pink Floyd problem. Thank you, 1 person. Everyone else listens to dubstep. And then I never liked it until one weekend. Something bad happened. I got really kind of depressed. And then I happened to listen to it, and it just made me feel better. Yeah, because dubstep just, I don't know, it reminds me, I don't know, it just makes me feel like music that you would listen to break stuff.
Did you break anything?
No. See, like when I was younger, I used to break anything. Right, whatever. Like hit something, break it. Now, if I hit something, I'll break myself. So it's like, not gonna think twice about it. Okay, do I want to get broken or do I want to? All right, anyways. So here, calculate the angle of refraction at the left side of the prism. So this is just going to be whose law? Snell. Not Snail, Snell. Right? Snell's law. So we just say N. Oh man, I'm writing crayons. Okay, so we say N1 sine theta 1 equals N2 sine theta 2. Right? So we say theta 2 is equal to the inverse sine of N1 over N2 times sine theta 1. Pretty straightforward. Okay? I don't know, whatever. I don't remember the sine of 40 degrees, but you take sine of 40 degrees times the ratio of 2. This is air, so there's like 1. So that's 1 divided by 1.6, because out here is N1 and this is N2, right? So it's whatever that is. So I'll just go like this. That way I don't have to use the calculator. Blah. And there we go. Sine theta 2, 1 over 1.6 and sine theta 1. You get 0.39, then you do the inverse sine of that and you get your answer, 23 degrees. Okay, remember when you're doing this, that 3 sig figs is all that you will ever need, right? Ever. Don't ever go 4, 5, 6. Don't act like a freshman and write down every number on your calculator. Right? Don't do that. It's not that they're going to specifically ding you, but when I'm grading and I see someone do that, to me that indicates that they don't know what the hell they're doing. Like they're just guessing wildly, right? And you don't want to make the grader think that you don't know what you're doing, because there are times when you might skip a step, and they're supposed to give a point for that step. And if they think that you don't know what you're doing, they're not going to give you the point. They're going to say, okay, this idiot just got lucky, right? But if they think you know what you're doing, then they'll be like, well, you know, they made this jump from here to here, I'm going to give it to them. So 3 sig figs, that's it. It's never more than that, right? In fact, if you just use gravity as 10, then stick with 2. I mean, how can life get any easier? 2 digits, right? And you can see this was an acceptable answer, 2 digits. Okay, so please remember that. Yeah. Okay, yeah, for some reason, high school teachers, well, I don't know, did your chemistry teacher ding you for sig figs? What?
Cameron did.
Cameron did.
He used too many. His max was like 3.
Yeah. What about Strom? Strom didn't ding you for sig figs? I'm sure Strom dinged you for sig figs. No?
I didn't have some.
I guess everybody had Cameron. Well, that's good. That's good to hear that Mr. Cameron does that. That's good. All right, next. Using the same prism, describe a change. So tomorrow, today Wednesday? Tomorrow and Friday. So tomorrow let's do, tomorrow's Thursday, isn't it?
Yes.
Tomorrow and Friday. But at least I think that's what I said. What came out of my mouth, I'm not entirely sure. We can go to the video. Roll it back. What? No. Let's see. We've only done 2011 and 2010, right?
Yes.
Okay. So the two homework problems for tonight. Let's do number 6s for both of those, or whatever. The last one, the nuclear part, whatever, atomic physics one. Actually, I think it's 7, isn't it? Oh, that's right. We did 11 and 11B, didn't we? Okay. So yeah, that's good. That's 3. Good. So let's do the last problem for 11, 11B, and 10. The last problem. So for 10, if I can show you, it will be number 7. And I think for the other two 11s, I think it's number 6. Yeah. Well, you tell me, what is this? A light wave comes in, an electron comes out. What is that called?
Alpha.
The photoelectric effect. Right? And when I say photoelectric effect, if you spent any time looking at the video that I made, or if you were here, photoelectric effect should make you think of a specific equation. Right? And then that should make you think, okay, that's work function, that's getting out of bed. I remember that analogy. Getting out of bed, that's to get the electron to the top. Right? And then HF, that's the energy of the photon. And then KE is going to be the energy of the electron. But anyway, I'm not going to coach you anymore. No. All right, so here, using the same prism, describe a change to the setup that would result in total internal reflection of the beam at the right side of the prism. Justify your answer. Total internal reflection at the right side. So basically, you have to adjust theta so that this angle here will, like this angle, theta 3, will get bigger to a certain point. Right? Because critical angle is sine theta c is equal, or, well, no. Yeah, sine theta c is equal to n2 over n1. Yeah, n2 over n1. You know how I know that here? Because this is n2, right? This is n1, because it's the air. This number right there has to be what? I'm not asking for a numerical value, I'm asking for a range. You should know that. If I tell you sine of theta is this, you know that number must be in what range? It's got to be between 1 and -1, right? This cannot be greater than 1 in magnitude. Does that make sense? So if I put n1 over oh crap, I did it the other way around. I should have flipped it. See, but that's what I'm saying. Like, I know that it's not right because this has to be less than 1. So it has to be the n1 over n2. Right? It has to be the air over this. So even if you don't know which one's n1 and which one's n2, when you're talking about internal reflection, you're talking about this light bouncing back inside. And so then you just say, okay, that means this, like, if it's going to go out of here, this, and this is the formula, this has to be like 1 over something, or it has to be less than 1. So my point is, it's like you don't even have to worry about which one's the n1, which one's the n2. When you're talking about this going to this, you know that that has to be true. Now, what about if I go from this to this, from air into that? Can I have total internal reflection? No. Right? Because when you actually follow the formula, when you actually follow the formula of total internal reflection, then that makes, okay, is it n2 over n1, n1 over n2? It's on your formula sheet. n2 over n1. When it's n2 over n1, that if you're coming from out here, then that flips which one's n2 and which one's n1. So it won't work. But anyways, okay. So we use this concept and we say, okay, what does this mean? What does total internal reflection mean? It means it bounces off inside there. And then this is just given by this. So sine theta c is going to be n2 over n1. Do you see what they're talking about? Because for part A, like this part over here, this was n1 and that's n2. But then for part B, it's like this became n1 and this became n2. And that's why this works. Do you see what that is? Because when they're talking about internal reflection, where are you starting? Where is the light starting? Inside the glass, or whatever this is made out of. Yeah, glass. So inside the glass is n1. Right? In the very beginning, n1 is outside the glass, because where did we start? Outside the glass. Right? So that was n1, and this became n2. But when you look at this reflection by itself, n1 is where you start, n2 is where you're going. And that's why this equation works. Yes? All right, well anyways, yeah, so all I have to say is we need to adjust this angle so that theta 3 equals the critical angle. Right? And then the critical angle is usually like big, right? Because you won't get internal reflection if you're shooting a light straight at the barrier, right? It's when you kind of angle it a little bit. So the more you angle it, then there's going to be a point where it totally internally reflects. So you would just say, I need to angle the incident beam so that happens. Let me see if they wanted actual measurements. I don't think so, because it's just a justify. Although you could justify through numbers. Yeah, okay, see? So you could do it either way. You could argue it both ways. So here is what, increase that, is that better? So here you can see they did this just by words. They said in order for that to occur, theta 3 must increase until it's theta critical or bigger. And then in order for that to happen, then blah blah blah, whatever must happen. Right? And then down here, they're saying this is the critical angle, and then they just use Snell's law to go backwards. So they said if this is the critical angle, they're basically saying something like this. Here's my triangle, and then if I want this to be theta c, or the critical angle, then that determines what this light, how the light comes through, right? So this will reflect. Actually, I'll use a different color beam. That's going to give me total internal reflection. So then, If that's true, then I can calculate whatever this angle of light is. And you can use the original drawing as your guide there. Right? So you see what I mean? Theta 3 has to be whatever it was, 37 degrees. So then from that, because of the geometry of this triangle thingy, then I know what theta 2 is. Does that make sense? If you know, if I give you theta 3, like say this is, well, let's do that. Let's say theta 3 is 37 degrees. What does theta 2 have to be? Go ahead and figure that out. If you draw the triangle, you'll get it like that. Somebody just realized. There's lots of papers.
Because for sure, yeah, actually I need as much of that air as possible. I just have to do the same.
All right, because of time, I'm going to show you. You see this angle, this thing right here? That's perpendicular to this side, right? Because it's the perpendicular. And then this is perpendicular to this side because it's the perpendicular. So what's this angle right there? Do you see this triangle? Like that? This angle is 37 degrees. What's that angle? Almost. That's 60. This angle right here is 60. You see that? So this is 120, yeah? If that's 120, this has to be 23. Well, 50, I think so. You see it? Just straightforward geometry. No? Yes? Questions? Okay, so anyways, that means this has to be 23. And if we know that's 23, then we can do this, right? Because then what we know is n1 sine theta 1 equals n2 sine theta 2. So we know sine theta 2 already. So we just say theta 1 is equal to inverse sine of n2 over n1 times sine theta 2. So we're just using Snell's law. So all we do is it's critical angle, then it's logic, whatever, geometry. So I hope you enjoy geometry. And then, boom, it's Snell's law. Okay, so I believe that's what they show us here. All right, 20, whatever, 22.7. But you see it. That's 37, that's 23, and then we can use Snell's law. Oops, just kidding. That's not you guys. Then the incident, is this it? Yeah, it is. Then the incident beam is now perpendicular to the surface. The glass is coated with a thin film that has an index of refraction of that to reduce the partial reflection of the beam at this angle. Calculate the wavelength of red light in the film, and then calculate the minimum thickness of the film for which the intensity of the reflected ray is near 0. So the wavelength, that part, this is when I remember this. I remember that people who did this, they were like, oh, I didn't know what to do. Oh, just relax and think for a second. What is the bridge between light out here and light in here? What is the thing that tells you the relationship between those two lights? What is the only thing in that diagram, the only number in that diagram, that connects or tells us light out there behaves this way, but light in here behaves this way. Dan, what is N? And what does that mean? What is 1.65? What is N? It is the index of refraction. What does the index of refraction mean? It's the ratio. So it is going to tell us how light bends because N is C over V. Right? So basically, V in the prism is going to be C over N. Right? So that tells us the velocity of light in here. And then since we know that V equals F lambda, and then both of these frequencies, like of these three things, which is the one thing that cannot change? F. Think about U. Can your speed change? Yes. Can the length of your steps change? Yes. You can make them small, you can make them long. Can you change? Theoretically, no. Right? Okay, even if you dress yourself up, whatever. So basically, what we're saying is basically F outside is equal to F in the. Let me say. F in the air is equal to F in the glass, right? And since F is equal to V over lambda, I say V in the air over lambda in the air is going to be equal to V in the glass over lambda in the glass. Claire speaking. Hey. I think he's taking an AP test. Oh. No, he's not here. Bummer. The only, well, being as he's in honors, the only one that I was aware that he would do is the B. Because I didn't know if you could do both at the same time. Yeah. Okay, thanks. Bye. Okay, so, right here, and then from this, right, we know that VA, right, this is C. Yes? Okay? And they tell us red light wavelength here. So we know this. This is given. So these two red things are given. And then what is the velocity in the glass? Well, we know velocity in glass is C over the index of refraction. Index of refraction of the glass. So this becomes C over N over lambda G. And then we're looking for lambda G, right? So we say lambda G is equal to C lambda A, lambda in air, over V. What's that? Yeah, we're in the first part of C. So then this becomes C on the bottom there, that goes on top, lambda A goes up, and then N sub G is down there. So that goes away. So lambda G is just lambda A in air divided by N.
Is it divided by that new thing or divided by N of the glass?
Yeah, the glass, N of the glass. So if we look at C, we get something like, oh, it's all crazy. What's that?
This one says N of the
Oh, in the film. Oh, that's right. Okay, sorry. Like I did it. I didn't consider the film, but it goes from the air to the film. So that's why this is N over film. But this is what we got here. So all they did is they used these two equations, this is what we did. We used these two equations to get this. Right? That's all that happened. Right? That's what we got. The issue was, I don't know, my brain I didn't read the film part, so I just did the class, but we needed to do the film first. Does that make sense? Yeah, so it's just, the logic that I said is all right. It's just the first thing that the light hits when it goes from the air is the film, not the glass. So all of our logic is fine. Okay, so then you just needed to use this end of the film right here. Okay, then calculate the minimum thickness of the film for which the intensity of the reflected ray is near zero. Intensity near zero. What does that mean? Intensity near zero. What does that mean, Brian? Intensity of light is near zero. You have no idea what that means. Stop thinking about physics. Just use common sense. The intensity of light is zero. What does that mean? Yeah, there's no light. Right? Like, I don't know, you guys get so wound up or you're trying to think about the physics part of it and you just freak out and then something that's obvious becomes non-obvious, right? When I told him, like, stop thinking about physics, just use common sense. And he's like, wait, intensity, zero, that must mean no light, right? So you do that. So if you see that it goes through a film and the intensity of the ray is near zero, what are we dealing with? What kind of a problem? What's happening in this problem? Light's canceling out. When does light cancel out? Yeah, it's something about this is out of phase, right? It's destructive interference. And I think that's what we'll see right here. Right? So what they're saying is that two thicknesses of the film equals lambda over 2. Remember this? Okay, it's just the path difference, right, or whatever that path difference, like when it goes through the film, like this, right, this right here is T. So we know that these two up here have destructive interference because they told us that the intensity was near zero. So that's where this whole thing comes from. 2T comes from this, and then lambda over 2 comes from destructive interference. And then we just figured out lambda. And let's say, for example, for the one above, part I, let's say you used lambda the glass. You're going to lose a point for that one. But then if you take that lambda and come over here, you'll get both points for this. You'll get all the points. Right? You can get points for a wrong answer. Because if that answer is correct based on your units, they'll give it to you. Alright, so anyways. Yeah, so then it's just a function of solving for t, which is pretty straightforward because everything was already known. Right, we know this. Check. Okay, questions? Okay. So there you go. That's that question. All right, and we go to this one. All right, so this cart moves. How much more time do we have? 10 minutes? Is that indeed 10 minutes? Or is that barely? All right, so here, this plastic cart is moving towards this. This is a metal loop. Okay, do you see what's going to happen? What's going to happen in this problem in general? Vivian. What happens when that metal loop enters that magnetic field? was thinking general, and she gave me a very specific thing, which is excellent. Right? She said flux increases. When flux increases, when a magnetic flux increases in a wire, what happens, Ja? Okay, so she started talking about current. Okay, so whose law is she thinking of? Lenz's law, because she's talking about current. Okay, what about Kevin? Who's the other law? And what does that law talk about? How's that? What about flux? Changing flux causes what? That's Lenz's law. Tiffany, who? What's the other law? Lenz's is one. Nope, not Ohm's. Right? Well, I'm not gonna. Don't say answers. Nelson? You're sitting next to the guy who just said it too. Mr. Dong? Okay, Faraday's law. Remember, Lenz's law talks about current. John told us that. Other people told us that. Faraday's law talks about what? Jody? That's Lenz's law. Faraday's law talks about what? Helen? No. It's about, it has something to do with electricity. Lisa? Van? And what? That is Faraday's law. Change in flux over change in time is Faraday's law. What does it tell us happens? What happens when you get a change in flux over change in time? It's one of your equations. What's that? Did you say average?
You get
M. EMF. Yes, you get M. EMF. Okay, that's kind of important. Okay, you need to know that a change in flux is going to do two things, and they're related to laws. Lenz's law and Faraday's law. This one is EMF, and this one is current direction. Those are the two things that happen. Lenz's law tells you the current is going to fight the change. Faraday's law tells you that you're going to get an EMF. All right, well anyways, on the figure, it'll indicate the direction of the induced current loop. So flux is going into the board, and it's doing what? Yeah, it's increasing, right? So if flux is increasing inside the loop, what do I need to do? I need to decrease it. So my fingers go out of the board inside the loop. And that means current is this way, counterclockwise. I think I drew it right this time.
Yes.
Okay, and why would I justify? I would say flux is increasing, therefore I must fight the delta phi, so then my B field, or whatever, is, I don't know, out of the board, out of the paper, therefore the current is counterclockwise. However you want to explain it. When the front edge of the rectangular loop is at 0.12, so that means when it's right here, that means there's 0.08 meters still outside. The speed is 3 meters per second. Calculate the following for that. The magnitude of the induced current in the rectangular loop of wire. So I'm just going to use E is BLV. Right? So I'm going to take 2 Tesla times the length of that wire, which is 0.1 meters, times the velocity, which is 3 meters per second. So then it gives me 0.6 volts. Oh, yeah, okay, they asked for current, thank you. We got 0.6 volts, and now I have to say I is EMF over R. So then I'm gonna get 0.6, and the resistance was 4. So I get 0.6 over 4, 0.15 amps. So 3, hopefully we were right. Yeah, there you go, counterclockwise. So B, yeah, we got a 0.15, excellent. Then we go to II, the magnitude of the net force on the loop. So now, if I have a current of 0.15 amps, then F is BIL, right? That's all. So B is 2 Tesla, current is 0.15 amps, and the length is 0.1 meters. All right, so that becomes 0.015, so it becomes 0.03,
Yes.
0.00.
No. 0.03.
So, yeah, that's right. So 0.03. Because this would be 0.3, then times that means 0.03. And that's going to be newtons. Okay? And then finally, at the bottom of this gibberish, later time the current loop are completely inside to determine the magnitude of the net force on the loop at that time. I would say, so I guess I just put F net equals 0, right? Because if the cart is inside the loop or inside the B field, then delta phi is 0. Therefore, no emph. Therefore, no current. Oh, I guess you could technically you'd say therefore no force. Okay, and that is it. Let's take a look just to double check. Okay, so we got our 0.03 right there. That's good. And then here, net force is 0 because there's no flux.